All right, let's dive into a math problem that at first glance looks, well, impossible. We're going to try and solve for x in the equation 1 to the power of x equals 12. Yeah, you heard that right.
So how in the world can 1 to the power of anything equal 12? I mean, we all learned this in like 3rd grade, right? 1 times 1 is 1. 1 times 1 times 1 is 1. You can do it a million times and it's still just 1. So where does 12 come from?
And yeah, that's probably exactly what's going through your head right now. 1 to any power is just 1. And you know what? In the world of the numbers we use every day, the real numbers, you're 100% correct. This equation should be impossible.
And it is impossible, unless
Unless the number 1 has a secret. What if that simple little number we take for granted has a hidden identity, a secret identity we can use to crack this thing wide open? Okay, so let's talk about this secret identity of the number 1. So let's stretch our brains a little bit. What if 1 isn't just that one little tick mark on the number line between 0 and 2? What if it could exist somewhere else in a different kind of mathematical space? Well, the key to this whole puzzle is one of the most beautiful formulas in all of math. It's called Euler's identity, and it tells us that the number 1 can also be written as e to the power of 2k pi I. It's just wild. This one little formula ties together 5 of the most important numbers in the entire mathematical universe. So let's break that down real quick. You've got e, Euler's number, pi, from circles, and I, the square root of -1. But the real superstar here, the game changer, is k. See, k can be any whole number, positive, negative, you name it. And what that means is there are actually infinite ways to write the number 1. Mind-blowing, right?
All right, now that we're armed with this secret weapon, let's go back to our impossible problem and see what happens.
Okay, step 1 is rewriting the equation. First, we're going to swap out the 1 on the left side with its fancy new identity, e to the 2k pi I. Then we do a clever little trick on the right side. Think of 12 as just 12 times 1, right? So we're going to replace that 1 with its own complex identity. But here's the catch. We'll use a different variable, n, instead of k, because there's no reason these two versions of 1 have to be the same. And just like that, we get our new equation to work with. Okay, so now that we've got everything set up, let's start actually solving for x. First things first, let's clean up the left side. You probably remember the power rule for exponents. When you've got a power raised to another power, you just multiply them. So we just multiply that x into the exponent. Boom, much simpler. Now, to get at that x that's stuck up in the exponent, we need to use its opposite, its inverse. And that is the natural logarithm, or log. So we're just going to take the natural log of both sides of the equation. Totally legal move in algebra. And to do that, we're going to need 2 trusty tools from our logarithm toolkit. First is the power rule, which is awesome because it lets us pull an exponent down and stick it in front. The second is the product rule, which lets us break up a multiplication problem inside a log into 2 separate logs. These 2 rules are going to do all the heavy lifting for us. So let's apply those rules. On the left side, the whole exponent just pops right down in front. Easy. On the right, we use the product rule to split log of 12 times e into log of 12 plus the log of the e part. Then we use the power rule again on that second piece to bring its exponent down, and now we've got this. And now for my favorite part, a really satisfying simplification. The natural log and the number e are like mortal enemies. They're inverses, so they just cancel each other out. That means that log of e is always just the number 1. How cool is that? So let's go ahead and replace every log of e with a 1. And look at that. Suddenly our equation is so much simpler, so much cleaner. We are getting really close now. All right, we're on the home stretch, the final step. To get x all by itself, we just have to divide both sides by all the stuff it's being multiplied by, that whole 2k pi term. Okay, almost there, but let's just tidy this up a bit. It's kind of considered bad manners in math to leave an I in the denominator, but it's an easy fix. We just use a little trick, where we can use the fact that I times I is -1 to get it out of there. And here we are, the solution. And look at it. It's not a simple number, is it? It's actually a whole formula. It's got a real part, that n over k, and then an imaginary part with I and the log of 12. Pretty wild. So we have this crazy looking answer. What does it actually mean? Well, it means our question doesn't have just one answer. It has a whole universe of them.
So let's just wrap our heads around this. The answer to what is x isn't a single number on a line. It's a complex number. And because you can plug in any whole numbers you want for n and k, as long as k isn't 0, of course, you get an infinite number of solutions. Every single one of them is a valid answer. What this really shows us is that a problem that seems totally impossible might just be waiting for you to look at it from a different angle.
It really makes you think, doesn't it? We just solved something that breaks a basic rule of math, all by stepping off the familiar number line. So you have to wonder, what other impossible problems out there are just waiting for us to find a new way to look at them?